One of the really nice features of the spin 1/2 quantum mechanical system is that while mathematically it's about as simple as quantum mechanical systems get, it can still be used to make predictions about the sorts of things that you could actually go and do in the lab with a moderate budget. Most of those experiments have to do with the behavior of spin 1/2 particles in a magnetic field, so let's see how that works exactly. The mathematical structure we're dealing with is the same as it has been for the past couple of lectures. We have three components of spin angular momentum: S sub x, S sub y, and S sub z. Expressed in terms of a basis of up and down, by up and down I refer to the eigenvectors or eigenstates of the z component of angular momentum. These Sx and Sy and Sz operators can be expressed as 2x2 matrices. These 2x2 matrices are usually written as the sigma x, sigma y, and sigma z Pauli matrices, which are essentially what you get if you remove an h bar over 2 from the matrix representation of the spin angular momentum operators. So we have these matrices. We know, for instance, the eigenstates of the S sub z operator. Since we're using those as our basis, we will have very simple expressions for the eigenvectors associated with the S sub z matrix operator. The eigenvalues, you know, are h bar over 2 and minus h bar over 2, and the associated eigenvectors are 1, 0, and 0, 1. The expression of the eigenvectors and eigenvalues for sigma x and sigma y are slightly more complicated. The eigenvalue structure for x and y angular momentum is the same, of course, h bar over 2 and minus h bar over 2. But the eigenvectors are slightly more complicated. For the x component of angular momentum, and you can do this finding the eigenvectors by any algorithm involving 2x2 matrices you want, the math is not that difficult, you get 1 over root 2 pulled out front for normalization, 1, 1 for the eigenvector associated with the positive eigenvalue, and 1 minus 1 for the eigenvector associated with the negative eigenvalue. For the y component of spin angular momentum, we get something that looks somewhat similar. 1 over root 2, 1, and then I for the other component, and 1 over root 2, 1 minus I. So we have 1, 1, 1 minus 1, 1 I, 1 minus I, and then 1, 0, and 0, 1. These eigenvectors and eigenvalues tell us pretty much everything we need to know about the quantum mechanical mathematics of spin angular momentum. From the physics perspective, what's interesting about this is that particles with spin angular momentum typically have a magnetic dipole moment, mu, that is directly proportional to their spin angular momentum. So if we're working with a particle with spin angular momentum, the proportionality constant gamma here directly tells us the magnetic dipole moment. You can think about magnetic dipole moments classically relatively straightforwardly. Suppose we have a large sphere that contains some mass and contains some charge. I don't know exactly how the mass and how the charge is distributed, but if this is rotating, it will carry that charge around in a circle, and it will carry its mass around in a circle, and therefore it will have both angular momentum and a magnetic dipole moment coming from the equivalent circular current of the charges as they rotate. I can simplify this picture a little bit by pretending that I'm just working with a ring of charge, or a ring of mass, rotating about the z-axis at some angular frequency omega. If I want to know the angular momentum of a rotating ring of mass m, suppose it has radius r, and angular frequency of rotation omega, I can write that down fairly straightforwardly. It's the moment of inertia of a ring rotating about its axis, mr squared, times the angular frequency. The magnetic dipole moment, mu, can be expressed similarly. The magnetic dipole moment of a ring of current is given by the area of the ring times the current flowing in the ring. So, pi r squared times the current. If I suppose that I have some charged particle that's rotating around this ring, the angular rate of rotation of that particle being given by omega, I can express the current in terms of the overall frequency and the charge carried by that particle. My magnetic dipole moment then becomes pi r squared for the area of the ring, times omega over 2 pi, the overall frequency, the number of times per second a charge passes, times the charge itself. So this is going to be a total amount of charge per second, or a current. Rewriting this slightly, I can express this as m r squared omega q over 2m. Essentially factoring out the angular momentum and leaving this rearrangement of constants. This then I can express as q over 2m times the angular momentum. And since what we're talking about is the spin angular momentum, I'm not going to write this as capital L, I'm going to write it as capital S. One interesting thing, and this is entirely a side note, this comment and the next slide is a side note. It's conventional to write this magnetic dipole moment as q h bar over 2m times the spin angular momentum divided by h bar, where this quantity is called the Bohr magneton. I'm telling you about this because this expression doesn't actually work. This Bohr magneton, while it is in some sense a fundamental unit of magnetic dipole moment, does not actually give you the dipole moment of a spinning electron. We have to add a fudge factor, which is called g. The g factor gives you sort of a correction to the proportionality between spin angular momentum and magnetic dipole moment. The reason g is so interesting is that it's something that we can measure to exquisite accuracy in the lab. This is the current measurement of the g factor associated with the electron spin magnetic dipole moment. I told you this is an experimental number, this is a measurement, and the uncertainties on this experimental value are really only present in the last decimal places. The smallest this number can be is 0.7 in the last two decimal places, and the largest this number can be is 3.7 in the last two decimal places. So this is our experimental number. Let me put an exclamation point on that because this is really an astonishingly accurate measurement. If you look at this number, this 2 here signifies 2 parts per thousand, already a pretty good measurement. This 9 signifies parts per million. This 4, parts per billion. This 2, where the uncertainty first arrives, is at the parts per trillion level. So we're really accurate with experiment to better than a part in 10 to the 12th. Imagine counting something and counting up to 1 trillion and only being off by 1 or 2. That's really an astonishingly accurate number. Theory hasn't quite caught up, but it's actually doing astonishingly well. If you go into relativistic quantum mechanics, you will learn that electromagnetic interactions can be treated from a quantum mechanical perspective as well. So quantities like the magnetic field or the magnetic dipole moment can be treated from the perspective of quantum mechanics. Knowing that they can be treated from the perspective of quantum mechanics, you can actually make quantum mechanical calculations of fundamental physical properties like this g factor associated with the electron spin magnetic dipole moment. Theory can get us this far. The more accurate you want to make your theoretical calculation, the more cumbersome that calculation gets. Essentially, you're adding up terms in an infinite sum. And the more accurate you want your result to be, the further closer to infinity you have to get. Current theoretical calculations have been carried out to this, the parts per billion level, and it agrees exactly with the experimental observation. So this is really an astonishing success of quantum mechanics, relativistic quantum mechanics in particular. But all of this doesn't really have all that much bearing to the sorts of experiments that I'm going to be talking about, the behavior of spin 1/2 particles in magnetic fields. So, getting back to our particle in a magnetic field. One facet of particles in magnetic fields is that if you have a magnetic dipole moment, there will be a magnetic energy associated with the relative alignment of the dipole moment in the magnetic field. The energy is given by the dot product of the magnetic dipole moment vector and the magnetic field vector, and this is, in some sense, a purely classical value. To make this a little more concrete, let's express the magnetic field as B naught, and I'll just give it a direction. Let's say it's in the z direction. The dot product, then, of our magnetic dipole moment, which you know is going to be associated with the spin angular momentum, then, since the magnetic field is only in the z direction, it will pull out only the z component of the magnetic dipole moment. So I'm going to have an S sub z in this expression for the energy. Now, energy, you've seen that before in quantum mechanics. We know the energy operator is the Hamiltonian. So the Hamiltonian under these circumstances is given by minus gamma B0 S sub z, where gamma S sub z is the z component of the magnetic dipole moment, and B0 is the strength of the magnetic field. Now, this expression, and I'll put hats on it for now, this is really involving operators. So reasoning by analogy from classical expressions, you can come up with quantum mechanical expressions, which may or may not work. Let's see what the implications of this expression for the Hamiltonian are. The Hamiltonian allows us to write a time-independent Schrödinger equation to find our stationary states. H psi equals E psi. Now, H psi is E psi. Well, we know what the Hamiltonian is now. We can substitute that in. Minus gamma B0 S sub z psi. If that's going to be equal to E psi, what we have here is an eigenvalue problem. Our operator is S sub z, our state psi, and our eigenvalue S sub z acting on psi is given by the eigenvalue minus E over gamma B0 psi. You know about the eigenvalue problem of S sub z, though. S sub z acting on some psi gave us plus or minus h bar over 2 times our eigenstate back, and we wrote our eigenstates as either plus or minus spin 1/2, either up or down. If I write this as up, I use the plus sign. If I write this as down, you use the minus sign. So we know about the eigenstates and the eigenvectors of the z component of angular momentum. That was what we used as a basis when we were expressing our Pauli spin matrices, for instance. What that allows you to do is identify the eigenvalues you get here with the energies. What that tells you is that the energy of, for instance, the spin up state is going to be minus gamma B0 h bar over 2, and the energy of the down state is going to be the opposite sign, gamma B0 h bar over 2. Our stationary states, therefore, are just going to be our spin up and our spin down states, the same sort of states that we've been working with over the past couple of lectures. The energies associated with these states are now different since we are allowing them to interact with a magnetic field. If I have a magnetic field pointing upwards, the up angular momentum operator, the dot product of the up arrow with the up magnetic field is going to be a positive number, so we're going to have a negative magnetic energy corresponding to this minus sign here. So there's really no mystery here among these energies and the states that we're working with. Knowing the stationary states and their energies, of course, we can make an expression of time evolution. We've done this sort of thing before. The time evolution of some general state psi, given in terms of just some constant a and some constant b, where here I'm going to simplify things by saying a squared plus b squared equals 0. I'll simplify this even further, actually, by the simplification here is that I'm not allowing a and b to be complex. A and b are purely real. But that's just going to be a relative phase overall, which isn't going to change our results significantly. So I'm going to write a as, there's a little bit of guesswork involved here, but to simplify the notation, you can write this as cosine of alpha over 2, and b as sine alpha over 2. The reason to use trigonometric functions at this stage is simply to enforce normality, since sine squared plus cosine squared is going to be equal to 1, not 0. Why do I keep writing 0 for normalization? Normalization requires the sum of these squares to be 1, not 0. And our trig functions are simply enforcing that normalization. If I express up and down in their basis, the basis of up and down, you know this is going to be 1, 0, and this is going to be 0, 1. So I can write this overall. My psi of t, then, is going to be the time evolution of each of these states. A times the time evolution factor that we're familiar with. I'll write this as a up arrow times e to the minus I e up t over h bar plus b times down e to the minus I e down t over h bar. This is the same sort of time evolution expression we've been working with for a while now. If I work in this basis, this expression, the up and the down are going to be replaced by their column vectors, which are simple. So when we combine them, we're just going to end up with the cosine alpha over 2 from our assumption about the form of A times e to the I gamma b naught t over 2, since our h bars cancel out, Likewise, sine alpha over 2 e to the minus I gamma b0 t over 2 is our expression for the column vector evolving in time associated with a general superposition of up and down with amplitudes given by a and b. If this is our time evolution, what sort of properties do we expect our state to have, and how will those properties evolve with time? We've done calculations like this before, for instance. Let's calculate the expected value of the angular momentum components to see how they evolve with time. The result is something called Larmor precession, and you can see it, for instance, by calculating the expected value of s sub x. S sub x, expected value, you can write that as some psi of t, the state under which we're calculating the expectation, s sub x, psi of t. Psi of t now being given by this complex column vector. The Hermitian conjugate of psi of t is going to be a row vector, complex conjugated form of this. So I can write that as cosine of alpha over 2 e to the minus I gamma b0 t over 2. And I'll put a comma in here to signify the space between the two components of my row vector. Sine alpha over 2 e to the I gamma b0 t over 2. Since this is an expression for the complex conjugate of this vector, I have to change the signs in the exponents here associated with the imaginary parts, which is why I've got a minus sign associated with my cosine term, whereas here I had a plus. Now we're evaluating an expression, the Hermitian conjugate of psi of t, on the left of the s sub x operator, to the left of psi of t. The s sub x operator, we know what that is expressed in this basis. It is given by h bar over 2, 0, 1, 1, 0. And then our psi of t is our column vector as before, cosine alpha over 2 e to the I gamma b0 t over 2, sine alpha over 2 e to the minus I gamma b0 t over 2. Doing the matrix vector product and then the vector vector product that results gives you something relatively straightforward. If you look at the structure of this, and I apologize for the messiness, hopefully it's still reasonably easy to see what all of these terms mean. The fact that the only non-zero entries in this matrix are the off-diagonal elements, what that is essentially going to do is swap the entries in this row vector. For instance, if you calculate the top entry of the row vector that results from this matrix vector product, it's going to be 0 times cosine, the cosine term, plus 1 times the sine term. So it's just going to be the sine term appearing in the top position. Likewise, we'll get the cosine term appearing in the bottom position. When I do the vector-vector product then, I'll end up with the cosine term from here associating with the sine term from here, the sine term from here associating with the cosine term from here. So both terms in my vector-vector product that results here are going to have a cosine sign in them, a cosine alpha over 2 times a sine alpha over 2. The complex exponentials combine in much the same way. I'm going to have a e to the minus something combining with an e to the minus something in multiplication, and an e to the plus something combining with an e to the plus something in multiplication. If you write that all out, and I'm skipping obviously a lot of steps of algebra here, our h bar over 2 carries out to the front, and we're going to get a cosine alpha over 2 sine alpha over 2 times, factoring that out since it's present in both terms, e to the minus I gamma b0 t. Since we have e to the I gamma b0 t over 2 multiplied by e to the minus I gamma b0 t over 2, the over 2's essentially cancel out when we add the exponents together. The other term is going to come in with a plus sign, e to the I gamma b0 t. Same form. You can probably tell what's going to happen now if you recognize cosine times sine from back in ye olden days when you were studying algebra and you were learning about trigonometric identities. That's why I had guessed alpha over 2 here. This is the double angle identity. What this means is that overall, this is going to simplify down to h bar over 2 times the sine of alpha. And the expression here, if you expand out the complex exponential as a cosine plus an I sine, you'll find that the sines cancel out. And we're just going to be left with cosine of gamma b0 t. So this is our expression for the time evolution of the x component of the spin angular momentum. It's oscillating with time. If you calculate the expected value of s sub y, you get a very similar expression, very similar algebra, only you'll be using the y Pauli spin matrix instead of the x Pauli spin matrix. And you get h bar over 2 sine of alpha times the sine of this gamma b0 t. So you can see what's going on. You have some amplitude here, h bar over 2 sine alpha times cosine for the x component and sine for the y component. This is a rotation of the expectation value in the xy plane. If you calculate the expected value of s sub z, you get a relatively simple expression, h bar over 2, which I should really write as h bar over 2, not some unintelligible squiggle, cosine of alpha is what you get. So the algebra here is simply expressing your state in the basis, expressing your operator in the basis, taking appropriate Hermitian conjugates, complex conjugate transposes, and doing matrix vector multiplications. That's all that's necessary to calculate expectation values here. And what you get is precession at a frequency given by this gamma beta. So effectively we have a frequency gamma, sorry, it's not a beta, it's a b, gamma b0. This is Larmor precession. And what it looks like is if I had some coordinate system here, you can visualize this as having some spin angular momentum vector at some angle alpha from the z-axis, and it's precessing around at a frequency omega given by this gamma beta 0. So the z component of this vector is remaining constant, and it's precessing around the z-axis. If you worked out what would happen for the case of a spinning charged ball in classical physics, you would find it actually has exactly the same behavior. This is expected because of some theorems in quantum mechanics that we studied earlier that tell you that the evolution of the expectation value obeys the classical behavior. So this is one sort of prediction, and this is the sort of thing that you can actually measure. The fact that this Larmor precession, incidentally, is at the base of what happens when you're making those extraordinarily precise measurements of that g factor I mentioned earlier. The Larmor precession frequency can be measured very accurately, and it's related to, of course, this gamma, which is associated with the, well, spin angular momentum. The other experiment that I want to mention is the Stern-Gerlach experiment, which is the result of another facet of the interaction of magnetic dipoles with magnetic fields. If your magnetic field is non-uniform, there is a magnetic force. This is the force that attracts two magnets together, and it stems essentially from the same sort of magnetic energy. The force, as derived from the energy, is given by the gradient of the energy, and we're talking about spatial gradients now. So your dot product of magnetic field, or magnetic dipole moment with magnetic field is an energy, and the gradient of the energy tells you how that energy changes as your magnetic dipole moves around spatially. So if there's a region of particularly strong magnetic field, it will be associated with a particularly high or particularly low energy. And the forces that result from that will tend to move the particle either towards or away from those regions of strong magnetic field, depending on the relative alignment. Either your magnets will attract or your magnets will repel. The reason this is important is that you can use this magnetic force to do quantum mechanical experiments. Suppose I have a magnet, and I'll draw it with, say, a north pole up here and a south pole down here. The reason the pole pieces are shaped the way they are under these circumstances when you're doing an experiment like this is you want to make a magnetic field that is non-uniform. When you have such a non-uniform magnetic field, you know you will be getting a magnetic force. Forces like this don't enter into quantum mechanics, however. The reason for that is if you think back to the Schrodinger equation, there was nowhere to put a force. The only thing that we could work with was potential. Well, we can work with potentials here. We can derive a potential associated with this force. And what that potential will do to particles with spin either up or down, which I'll write now as plus or minus, is it's going to change it from, instead of just being gamma b0, to minus or plus gamma b0 plus some alpha z. So instead of just having an energy associated with the magnetic field, we're now going to have an energy associated with the gradient of the magnetic field as encoded by this alpha parameter. The larger the gradient of the magnetic field, the larger the force, and you can think about the force here just simply resulting from a potential that varies in z. But it varies with z in such a way that the orientation of the dipole moment, pardon me, the z component of the spin angular momentum enters into the energy expression. If you work out what the time evolution factors look like then, they look like something like e to the I e plus or minus t over h bar, as before. But since this energy now has some spatial variability in it, our energy time evolution factors end up looking like plus or minus I gamma t b naught over 2, same as before, and e to the plus or minus I alpha gamma t over 2, all multiplied by z, and I've forgotten an I in this exponent here. So the fact that there's some z dependence to our energy now means that there will be z dependence in our time evolution of energy. And if you compare, for instance, the fact that we have an e to the I k z here, essentially, this is going to look like an e to the I k z, plus or minus. This looks like z momentum. This is not an especially rigorous argument because I have not actually expressed the wave function as a function of both position and spin. Doing so makes this math a little bit more complicated. You can look in the textbook if you want a slightly more complete derivation here, but conceptually what you need to understand is that a spin oriented in the downwards direction is going to be deflected upwards in this magnetic field, since it's going to be essentially attracted to the regions of high magnetic field. Magnets that are aligned with each other attract, whereas a spin oriented upwards is going to be deflected downwards in this magnetic field. So if I have some unknown particle here, a particle with unknown angular momentum, and I send it into this magnetic field, quantum mechanics now tells us that it will be either deflected up or deflected down. If I have a particle detector here that I can move up or down, or if I have a sheet of film that will be activated when these particles hit it, I will see a blob here and a blob here when I repeat this experiment many, many, many times. The particle, as it enters this region of magnetic field gradient, experiences a force and picks up a momentum that is going to depend on the amount of time it spends in the region where the magnetic field has a gradient. You know quantum mechanically that the only allowed states of this z component of angular momentum are either up or down, essentially. So you're going to get a deflection either up or down. You might ask why I'm only talking about up or down here. Why not the x or y components of the angular momentum? Well, if you think back to the previous slide where we were talking about Larmor precession, you know if there's some x component of the angular momentum, it rotates around in the xy plane very rapidly. So essentially any net force you might experience due to x gradients of the magnetic field and x components of the angular momentum will very rapidly cancel each other out since we're averaging over many, many, many cycles. The Larmor precession frequency is typically much higher than the amount of time it would take the particle to traverse this region of magnetic field gradient. So this experiment here, which is typically done with silver atoms, for instance, aggregate particle with a summed angular momentum equal to 1/2, such that we can treat it with the formalism we're using for the spin 1/2 system. As that silver atom, being neutral, traveling relatively straight through the magnetic field, it will only experience a deflection due to its magnetic dipole moment, which, as you know, being mu given by gamma s sub z, will obey the quantum mechanics of s sub z. We will only see two possible outcomes. So this Stern-Gerlach experiment gives us something that's deeply non-intuitive if what you are expecting is the classical physics result, which says that, well, we're going to have a random distribution of initial magnetic dipole moment vectors over here, and as they travel through, we're going to get essentially a broad distribution of positions, a broad variety of deflections of that magnetic dipole moment. This experiment was first done in 1922, and really was very important for kicking off the development of quantum mechanics. Quanta had been studied a lot before 1922, but this is before that famous picture that I showed you in the very first lecture in this course, the Solvay conference, that was taken more or less around when quantum mechanics was first developed. That was in 1926, 1927. So this is a very obvious experimental indication that something is very wrong with classical physics. And now we know how to explain it using the formalism of the spin 1/2 quantum mechanical system. To check your understanding of all of this, here are a couple of questions about what might happen to particles either spin up or spin down in various magnetic fields.